Araújo.
Araújo.
Araújo. And the title of the talk is Bell's Theorem, Many Worlds, and Quantum Key Distribution.
Okay, thank you for the introduction. Thanks, Lev, for organizing this nice conference. Yeah, I'm afraid there's going to be a kind of a break with regards to the previous talks because these are going to have a lot of equations. I hope you like equations. So the motivation for the talk is that many authors, when writing about many, claim that Bell's theorem is simply irrelevant because it depends on the assumptions. The measurements have a single outcome, and this is just not true. So we just ignore it. No, doesn't matter. But I mean, this is a bit uninteresting. Can't we formulate a version of Bell's theorem that just doesn't exclude many words by assumption, that actually says, tells us something? And in more practical terms, I mean, I care a lot about it because I work with quantum key distribution. So the security of this acronym is a device-independent quantum key distribution. Is the most powerful, most secure version. It relies on the violation of a Bell inequality. But then, if a Bell's theorem doesn't apply, is it just not possible to have device-dependent quantum key distribution? So I'm going to give a non-pedagogical. But come on, this is impossible. Hello, this works? Okay. I'm going to give a non-pedagogical introduction to Bell's theorem because I assume that everybody is like vaguely familiar with it. But the idea is that you have two observers, Alice and Bob, that are space-like separated, and they make measurements that depend on settings X and Y, and they give outcomes A and B. And then they estimated these probabilities P of AB given XY, and they evaluated this functional over them, which is called the Bell inequality. This is upper bound by some value called L, which is like the local bound or the classical bound and so on. And this inequality is violated in quantum mechanics, and then this gives a rise to a lots of discussion about what it means. So quantum mechanics is non-local or non-classical, and then some people even say, oh, it's not real or something like this. Okay? But then, okay, what is this local bound? What is this classical bound? How do we prove this inequality? Usually, the starting point for a proof of Bell's theorem is the assumption of factorizability that I have written there. That like when you condition the probabilities on this additional variable lambda, which is the information that should be in the common past of Alice and Bob, that it can be like the quantum state in the case of quantum mechanics, or the value of a hidden variable if you're thinking about the hidden variable theories, but it's very generic. It's like anything in the common past. Then they should factorize like this. And from this equation, getting the Bell inequality is just algebra, so it's not the interesting part. But the interesting part is how do you justify this assumption? How can you get this factorizability? So there are three ways in the literature. The simplest way is from the assumption of like a single word determinism, that you have like a single outcome, and this outcome is deterministic, and then it factorizes, or of course, if you add together no actual distance. This is like very simple and works very fine, but people don't like assuming it because determinism is a very strong assumption. And it's also clearly not true, so it's a bit hard. Like, why should we assume something that's not true? I'm going to get there. And then another way to get it is assuming Reichenbach's principle, which is grosso modo, saying that when we don't have like a direct cause from one to the other, then the probabilities must factorize when we condition on the common past, which is essentially the statement of factorizability. But again, I don't like this assumption because Reichenbach, he posed his principle only for macroscopic systems. or motivated by error of time and thermodynamics and so on. So there is no reason to think it should apply to quantum systems to start with. So why should we assume that? Why should we be bothered that it fails? And in fact, there is a quantum Reichenbach's principle, and it doesn't imply factorizability. So, but then there's the third way, which is from the assumption of local causality, and I think that's the good way, because local causality is something that we want to be true, that we care about a lot of the violation, and it should also be true in quantum mechanics. And I want to emphasize here, with a quotation by John Bell, that factorizability is not the formulation of local causality, but a consequence thereof. So we really have to start with local causality to get something that is interesting, something meaningful. Okay, so what is local causality? So this is a space-time diagram. So here you have like Alice. A is like a Alice experiment, and you have her past light cone and her future last light cone, and Bob that is like space-like separated from her. Then local causality says that the probability of some event in A only depends on the stuff or events that's going to be precise later that is in her past light cone. So in particular, it's not going to depend on anything that happens at Bob's side. So we can condition the probabilities additionally on Bob or whatever Bob does, and it shouldn't make any difference. So this equation should be satisfied. Okay, and from this assumption, it's very easy to prove factorizability. You start with this probability, this correlation conditional lambda. That's what we're interested in. And then we just use like a regular rule of probability. This is nothing that I'm doing in the first line. Just to separate it like in some probability from Alice and some from Bob. And then on these two terms, I apply local causality that like from the probability of Alice, I remove the conditioning on B and Y because that's space-like separated stuff. And then the probability should depend on that. And then from Bob's side, I remove the dependence on X because that's on Alice's side, so it shouldn't depend on that. And then on the bottom, I get factorizability. And from that, I get Bell inequalities, as everybody likes. Okay? So then, if you think of this happening in a single word, what's going on? So let's say we are interested in the outcomes 0 for both. So A equals 0 and B equals 0. And the settings are just going to be the computational basis, the Z basis, or the up-down basis. And the lambda is just a quantum state, which I put there a maximally entangled state. Then the probability that Alice gets 0 condition that Bob gets 0 is just 1. And that's not equal to the probability of only Alice condition on her measurement alone, which is 1/2. So quantum mechanics violates local causality in a single word, as everybody knows. Now, in many words, it's much more interesting because now what is B? What is this Bob's outcome? This doesn't exist. Now we are from the point of view that Alice hasn't heard her measurement yet, and she's considering what's the probability that she will get 0, or that the fraction of her future selves will observe 0, and then she can condition on whatever happened at Bob. But according to many words, what happened at Bob is just that Bob got entangled himself to the quantum state they shared. Okay, so yeah, Alice can condition herself as much as she wants on that. Is not going to change anything. The probability she is going to observe 0 is still going to be 1/2. So in many words, quantum mechanics respects local causality. So I'm just showing the equations from before, putting values there. So the first equation there is to respect now the probability of AB there is not the correlation of probability of 0, 0 anymore, but the probability that Alice gets 0 and Bob gets to this entangled state. Yeah, this is just 1/2. And so on, and so on, and so on. And local causality is respected, and then the probability is even factorized. So factorizability is respected in this useless sense. But the point is, like, when do these correlations exist? When is it meaningful to talk about the probability of 0 and 0? instead of the probability of Alice getting 0 and Bob getting an entangled state? Well, only in the future light cone, as Brown and Timpson put, we can only think of the correlations obtaining in the overlap of the future light cones of the measurement events. They do not obtain before, and a fortiori, they do not obtain instantaneously. Yeah. So yeah, I think it's clear. Now, if you think about now on the intersection of the future light cones, now it's meaningful to talk about the probability of 0, 0. And then, yeah, there's 1/2. Okay, and then if we do this, this chain rule or Bayes theorem or whatever you want to call it, yeah, it still works fine. But now, does it make sense to apply local causality? Because now the B and X and everything is in the past light cone of this point in the future that we're considering. So factorizability is not respected because the marginals are still 1/2 and 1/2, but the correlator is 1/2. But so factorizability is not respected, so it doesn't bother us. But now I think there's an objection that many people here would raise, is that at this state, the Bob entangled, is a global object. It's defined on Alice's and Bob's locations, and we cannot say that space like separated from Alice. So how can we even like formulate the local causality for that? Like Bell formulated local causality in terms of local variables. And the quantum state is clearly not one, it's a global object. But yeah, there is a way to solve this, which is going to be main talk by Charles, and sorry, I forgot the other guy's name. That you can assign local variables in quantum mechanics, in many words. So the idea is essentially by using the Heisenberg picture, because the dynamics are local. So in the Heisenberg picture, we fix the quantum state should be some standard initial state. In the case, I call it 0. And then let U be the unitary dynamics. And then I define like a global variable for everyone. It's going to be this C of U. And this C is the Choya-Minkowski isomorphism of U. I assume that nobody is familiar with that. But don't worry about it. It's just a convenient way of rewriting U. So just, yeah, how do you write the matrix? It's just like a simple function of U that I need this function just to get a convenient mathematical expression. And then the interesting thing from this formula is, because up to now, I just wrote down the dynamics, that I can write the local variables. And they're just given by these expressions. You just take the partial trace over the output system of one party, and so and vice versa, and you get the local variable of Alice and the local variable of Bob. And these local variables are complete in the sense that the global variable is a function of the local variables. In fact, it's just a product of them. And the local variables, they are local in the sense that now if I define the local variable for Alice, it's not going to depend on whatever Bob does. So Bob can apply any unitary V on his side. It's not going to change Alice's local variable. And again, Alice can apply any unitary S on her side. And it's not going to change Bob's local variable. So in this way, we can assign the local variables, and then we can evaluate local causality in the way that Bell actually postulated. Yeah, and you see that it works. It's satisfied. But I still don't like that, because this only shows that local causality is meaningful in many words, but doesn't imply the Bell inequalities. But we still don't know what implies the Bell inequalities, and what does evaluation of a Bell inequality even mean. There is a lame answer that we can give, that we just add a single outcomes assumption in addition to local causality, and then we obtain local causality, we obtain the Bell inequalities, and the evaluation of the Bell inequalities are going to imply either non-locality or the existence or many words, or the existence of multiple outcomes. And this is defended, for example, by these people. But we can do better than that. So after Alice and Bob meet in their intersection of their future light cones, they can ask whether someone could have predicted with certainty the outcomes that they got. So the probabilities they have are this P, B of a given XY. And then if somebody could have predicted them, then there exists this decomposition that you can write then as a convex combination, this P of E with some probability condition on E, such that when you condition on E, the probabilities are always either 0 or 1. And then this E is like the extra information you need to predict the outcomes. Because in general, for Alice and Bob, the outcomes are still going to be probabilistic, but one can think that no, maybe they just look probabilistic because there is some extra information that we need to predict it. And if I had this information, they would be 0 and 1. And if it's possible to have this information, maybe they think that somebody has the information. And I'm worried about the scenario of quantum key distribution, that there is some enemy or eavesdropper that is trying to predict what they got, and with that, hack their communication. So is this possible in principle? So I call this assumption that this happens predictability. Now, if you assume a predictability and no action distance, then we can prove factorizability. Like from the first line, I just get this probability condition on E. Now it just separates into a product of A and B, and this is a completely trivial statement just because 0 times 0 is 0, 0 times 1 is 0, and 1 times 1 is 0. So the fact that they factorize in that sense is pretty much nothing. And then for the second line, I still want that the probability of A, like now in this case, a marginal doesn't depend on Y, and B doesn't depend on X. So now is a weaker condition than low causality, is a so-called no action at a distance. And then we get Bell inequalities again. And therefore, a violation of a Bell inequality means that either predictability or no action at a distance is false. No? Then, I'd like to show a couple of examples. Now, okay, so I'm going to show one example and then I'll skip it, the other. Okay, so let's say they're going to make the measurements in this state that is correlated, but classically correlated. It's a separable state. And they both are making it in the computational basis. And then the probabilities they get are given by this expression, which is clearly factorizable. And those, some eavesdropper could have predicted it. But how can it do the prediction? Then let's say we have the expression there. The eavesdropper has the purification of this state. That it sometimes was 0, 0 and sometimes 1, 1 because it was actually entangled with another subsystem that's in possession of the eavesdropper. And now, so there's essentially in each instantiation of the experiment, there are two words. One where the eavesdropper has the 0 and another where the eavesdropper has the 1. And now, after Alice and Bob do the measurements, they all end up in these words of the eavesdropper. So the eavesdropper 0 knew that they would both get 0, and the eavesdropper 1 knew that they would both get 1. So it gets quite a bit more complicated if we consider the case where they can make measurements in two different bases, but I'm going to skip that in the interest of time. And then, I'd just like to conclude that low causality is meaningful in many words. It just doesn't imply Bell's theorem. And the violation of a Bell inequality in many words implies unpredictability. And those, quantum key distribution is safe. Yeah, I can do that one.
Hi, thank you for your talk. It was very interesting. I was just wondering, as far as I understand, Reichenbach's rule means that you have to explain or causally explain correlations by a common cause if you have no causal connection between them. So it seems to, so I was under the impression that if you don't believe in Reichenbach's rule, then you don't have any problem with the Bell correlations because you don't even want to explain them. You don't have any necessity to explain them.
No. This is not true. Like Reichenbach's principle is much stronger than that. It's not only that you have to explain correlations. It's that if you don't have a common cause or a direct cause, then the correlations have this specific form. They must factorize. So this is what Reichenbach calls an explanation. This is what matters. And then I'm saying that I don't care about the lack of this kind of explanation, but I still want an explanation. But in the case of quantum mechanics, I don't care about a Reichenbach explanation failing, because we have the quantum Reichenbach principle. We need to have a quantum common cause. But what bothers me is the failure of local causality.
Doesn't Bell theorem work like this, that you have the non-factorizing empirical probabilities or the relative frequencies you get from the data, and then you want to explain them so that you have a model for them which factorizes them. So if you don't have this necessity to factorize them, I mean, what tells you that they need to factorize? Isn't this exactly Reichenbach's principle?
Yes. That's why I'm saying it's a bad assumption, because we shouldn't care about the factorizing. That's why I'm defending that the good assumption to use in Bell's theorem is local causality.
Okay, thanks.
Very nice talk. I just have a quick question about predictability. So you essentially say, if we can essentially write it as a sum, where E can always guess it with 100% chance or 0% chance, then it's predictable. Don't you think it's a bit strong in QKD, where maybe we're okay when Eve guesses it right with 95%?
Yes, of course. If you want to do like a series, QKD, we need quantitative statements. But I just wanted to show like the conceptual version that if they don't violate the Bell inequality, then it's over. Then they cannot do anything. If they do violate the Bell inequality, then we need to be quantitative and estimate exactly how much. And I mean, actually, my day job is exactly estimating how much Eve can predict, but I thought it wouldn't be the point here.
Okay, thank you very much.
So at one point, you moved to a description in terms of this complicated
Deutsche hidden descriptors.
yeah, and I was worried. You were saying this is a Heisenberg picture?
Yes, kind of.
Okay, so in the Heisenberg picture, usually you have to define what measurement is going to be performed, and then the operators corresponding to that measurement are propagated backwards in time.
Yes, but we can do better than that. You don't need to specify the observables. You can just use the this version that when U is the entire dynamics, that is, and then if you have the entire dynamics from that, you can recover any observable you want. So the original version by Deutsche and Hede, they use the specific observables, but that's pointless. It just makes things more complicated.
Sorry, it's a very basic question. It was a really interesting talk, and I'm just not sure I followed everything. So predictability and local causality are just independent assumptions. You can have all four options, that this one is satisfied and the other not. So you could have predictable but not locally causal, and vice versa.
Well, local causality is always satisfied in many words. So I was wondering, like, from which assumptions can you derive Bell's theorem? Like, you can get a Bell inequality. They are meaningful in many words. And my choice was to use predictability together with no accidental distance. I mean, you can also use local causality. I just use no accidental distance instead because it's a weak condition.
Okay, thanks. But in principle, you could have predictable theory which violates local causality.
Yes, you could, but I'm not sure if there will be much interest in those theories.
Yeah, maybe I'm just curious to understand the,
Ah,
how
the
the assumptions
logical
are related.
implications. Yeah,
That's
no,
all.
they are in principle independent. Yes.
Say that this is lame because many worlds option doesn't really say much.
Yeah, you don't learn anything. You just have like an extra assumption. Okay, it's many words or not, and that's it. And also they didn't treat this properly. Like to do like the proper proof of the theorem, you should be able to like do the derivation without assuming single outcomes, and then after that put the single outcomes and see how it collapses. But they just like assume single outcomes in the beginning before doing anything. Yeah, and then it's really just not any different from a regular demonstration of Bell's theorem.
Thank you.